So, hello everyone, welcome to class 12. Today we will be continuing our discussion on what we have started in the last class, which is trying to look at crystal systems, their classification. We said we can classify crystal systems into 7 different crystal systems, but the way they are classified is not based on their unit cell lattice parameters and unit cell lattice, the relation between these unit cell lattice parameters, which is A, B, C, alpha, beta, gamma, and the angles between alpha, beta, gamma, and whether A, B, C are equal or unequal, and so on and so forth. So, you may have seen some classification based on these criteria. However, the more fundamental classification comes from underlying symmetry, and from symmetry we can derive these constraints, right. So, that's the exercise we have been embarking on so far. So, we said in a triclinic system the only sort of symmetry that one can think of is 1 and 1 bar. So, it can just have an identity or an inversion, and having an identity or inversion does not impose any sort of restrictions on the axis, on the coordinate axis or the axis of the unit cell, the preferred unit cells. As a result, we ended up deriving that A not equal to B not equal to C, and alpha not equal to beta not equal to gamma not equal to 90 degrees, right. So, these sort of constraints just come from underlying symmetry. Now, then we moved on to monoclinic systems, and in monoclinic systems we say that there is at least one two-fold axis of symmetry or one 2-bar fold of sorry, not at least, there is only one two-fold axis of symmetry or only one 2-bar fold axis of symmetry, and 2-bar fold axis of symmetry is nothing but mirror. And so using this we could derive that so this would mean that a couple of axes should be perpendicular to each other. A couple of axes are not perpendicular to each other, whereas the others are perpendicular. So, let us say gamma is not equal to 90 degrees, or by convention we take gamma as greater than 90 degrees, and alpha equal to beta equal to 90 degrees, right. And there is no constraints on the size of the vectors, right. So, that we just did by a dot product operation between different components of vectors before transformation and after transformation using a two-fold rotation. Okay. So, then we said we moved on to the next system, which is the orthorhombic crystal system, and in orthorhombic crystal system we stopped at a stage where we said it is not just one two-fold axis of symmetry, but you have combination of two-fold axis of symmetry. If I have a two-fold along 1 0 0, I will also have a two-fold along 0 0 1, and later on when we are actually doing point groups, I am going to say that if I have a two-fold along 0 0 1 and two-fold along 1 0 0, I am going to I mean you can, this is an easy thing to show, this means that there is a two-fold along 0 1 0, right. So, if I have two two-fold axes, that is equivalent to having 3 two-fold axes, right. The proof is easy, right. So, if I just look at the transformation matrix of 2 0 0 1, that is nothing but so along the z axis I am not going to change the direction, the sign of, so z goes to minus, z goes to plus z, x goes to minus x, and y goes to minus y, right. And if I have 2 1 0 0, there I have, this is the transformation matrix 0 0 minus 1, right. And I am going to tell you when I do point groups that if I multiply two operations in a group, then I should get a third operation which is also which also belongs to that group, right. So, that is, so here I am just this, I call this operation P, I call this operation Q, and if I multiply P and Q, I should again get another operation which is in the group itself, right. So, again I will postpone that discussion to when I start doing point groups, but for now so if I just multiply P and Q, what I get is so this is minus 1, this is 1, this is minus 1, this is 0 0 0 0 0 0, and that is nothing but two-fold axis along 0 1 0, right. So, if I have a two-fold axis, right, so let me write it down. If there are two orthogonal two-fold axis of symmetry, a third one comes for free. A third orthogonal two-fold axis comes for free, right. So, it is there, right. So, just because I have two two-fold axis of symmetry, there should be a third one, right. Similarly, if I have two mirrors, perpendicular to each other. So, I am just going to say this mathematically now, and I am going to actually show you in terms of what are called stereograms later when I start doing point groups. An orthogonal, not a mirror, but an orthogonal two-fold axis comes for free. In other words, if I have m along 0 0 1 and if I have m along 0 1 0, right, which is m is in this case the normal vector to m is the 0 0 1 vector, which means m itself is the 0 0 1 plane, if you know a bit about Miller indices. So this is the other mirror which is perpendicular to the first mirror, but it is like this. But this plane is a 0 1 0 plane and this plane is a 1 0 0 plane, right, or 0 0 1 plane, right. Now, if this exists, what I get free of cost is a two-fold axis, but this two-fold axis is going to be about 1 0 0. Okay. So, okay. So, these are the systems, right, that we are going to look at. Now, if I have only one m or one two-fold, okay. So, if I have only one two-fold axis about 0 0 1, in the discussion on ensuing on monoclinic systems, we said this means that my gamma is not equal to 90 degrees, that is okay, but alpha should be equal to beta should be equal to 90 degrees, right. But I am saying it is not just one two-fold axis, I have two or more than two, actually three two-fold axis of symmetry, right. So, let us go back to three two-fold axis of symmetry. Okay. So, then if I have another two-fold axis about 1 0 0, that means now my alpha is so alpha does not have a constraint, the constraint I will just write the constraint, right. So, gamma not being 90 is not a constraint. The constraint is alpha equal to beta equal to 90 degrees. Here the constraint will be beta equal to gamma equal to 90 degrees. So, if I have two two-fold axis of symmetry, my constraint then turns out to be alpha equal to beta equal to gamma equal to 90 degrees, and that is nothing but, and then there are going to be no constraints on ABC or the magnitudes of ABC, which I am from now on I am just going to represent magnitude of A, magnitude of B, let me write it properly, representation. I am just going to say magnitude of A as A from now on, magnitude of B as just B, magnitude of C as just C. These are the unit cell vectors, right. So, A, B, C are the unit cell vectors. Okay. So, there is no particular constraint on A, B, C. So, that we just represent by saying A does not in general need to be equal to B not equal to C, and that will give me a unit cell, which is so in general A it is going to be a cuboid, right. So, that is what we said. So, cuboid is a three-dimensional rendition of something that looks like a rectangle in 2 dimensions, right. That is going to be my unit cell with all these things being my lattice points, okay. And so the only constraint is that alpha equal to beta equal to gamma. So, gamma will be, this is one angle, this is the other angle, and this will be gamma, right. So, that is gamma, okay. So, in general, so this is a cuboid sort of unit cell, which is called orthorhombic unit cell. Okay, or the crystal system is actually an orthorhombic crystal system. Okay. After orthorhombic crystal system, we go to a tetragonal crystal system. Now, a tetragonal crystal system has one four-fold axis of symmetry. So, I am going, I am postponing the discussion on three-fold axis of symmetry, because that is slightly in terms of the axis involved, we don't have orthogonal, I mean, so we go to axes that are at 120 degrees with respect to each other. So, we will do that at the end, but now after two-fold, right, I am going to a four-fold axis of symmetry. So, I am ignoring the three-fold and six-fold for now, I will do that at the end. Okay. So, I have a four-fold axis of symmetry, and I just have one four-fold axis of symmetry, only one four-fold, right. As you will see later on, I can add, but not another four-fold axis of symmetry. I can add another two-fold axis of symmetry or something else, but not a four-fold axis of symmetry, right. So, I have only one four-fold axis of symmetry. Right. Only one is the important thing. Okay. So, now if I have a four-fold axis of symmetry, what does a four-fold axis of symmetry do? If I have x, y, z, right. So, x, y, so x is along a axis, y is along b axis, and then z is along c axis, right. So, about c axis, let us say this is about c axis. I have a four-fold axis of symmetry about this axis is coming out of plane, right. So, if I have a four-fold axis of symmetry, my x, y, z sort of, x goes to the y position, y goes to minus x position, and so on and so forth. So, at so the a, b, c coordinates will then be minus y, this gets transformed to minus y, x and z, z does not transform, right. Okay, so what is the matrix of transformation of a four-fold 4, let us say 0 0 1 is nothing but my x goes to y, so that will be 0 1 0 minus 1, or the other way around, sorry. So, it should be 0 minus 1 0 1 0 0 0 0 1, right. So, so it is no longer it is no longer only the diagonal elements that are there, but now you start having off diagonal elements, So, the new y coordinate has x in it, the new x coordinate has minus y in it, right. So, as a result, this is the transformation matrix. Okay. Now, so R, if R is x a plus y b plus z c, right. So, I mean, so the way this transforms after transformation, this is along a axis. So, I have x vector, and this is along b axis, I have y vector. So, my a, so the x goes here along the b axis, and my y goes here along the a axis, right, along minus a axis rather. So, this is the a axis. Okay. So, that is my transformation. Okay. So, now if R is x a plus y b plus z c, then R prime, which is after transformation, after one four-fold rotation, will be what is it, minus y a plus x b plus z c, right. Now, if I do two four-fold axis of rotation, I have R double prime, that will be again it's a two-fold axis of rotation, right. So, that will be minus x a minus y b plus z c, and if I do three four-fold axis of rotations, that will be R triple prime, that will be this time y a minus x b plus z c. So, these are the four vectors I get by doing four-fold rotation, right. But all these four vectors, there is four-fold axis of symmetry, it is not, so all these 4 points should exist, and the environment about them should be exactly the same, which means now I can do my dot product business, and I am going to say that so R so let us say I take the dot product between A and B. So, x y A dot B, right. So, in R should exactly be equal to, which because so I have just there is symmetry. So, the environment about these things should exactly be the same. So, even if I transform, the dot products between the corresponding components should remain the same, right. So, should be equal to minus y x A dot B. So, as a result A should be perpendicular to B. Okay. Similarly, you using one of these other vectors, you can show that B is perpendicular to C and A is also perpendicular to C. So, what you have is a alpha equal to beta equal to gamma equal to 90 degrees. Okay. Okay. The other thing, however, is so here so I am not going to mathematically prove it, but I am just going to say that x now so transforms to the vector A, right. So, transforms to the vector so transforms to y, right. Since there is fourfold axis of symmetry, that means so even after transformation the length of the vector here should exactly be the same as the length of the vector there. So, if I say that this is x A, that should be x B, right. Which means that the unit cell vector lengths of the unit vectors of A and B should exactly be the same, otherwise you are not going to satisfy the constraints of symmetry, right. So, just because so I am exchanging x and y here, right. So, I between R and R prime, if I exchange, since I am exchanging since x and y are being exchanged, which means x along A, x units along A axis and x units along B axis should exactly be the same, right. So, what it means is x A by symmetry, after symmetry x A turns to x along B axis, right. But I am going to say that the vector length of x A should exactly be equal to the vector length of x B, which imposes the constraint that A mod A equal to mod B, or in other words I am just going to call this as A equal to B, right. So, you have an additional constraint. So, if my axis, if my fourfold axis of symmetry is the C axis, right, alpha equal to beta equal to gamma, that I just get from doing the scalar product, right. So, after symmetry the scalar product should be the same, any mathematical operation between components should be should yield you same results, but I am also going to say additionally it is not a twofold axis of symmetry, right. So, you are exchanging the component on the A axis towards the B axis, and as a result these lengths should be the same. If these lengths are the same, then you have the additional constraint that is only possible for all vectors, right, only if A equal to B. Okay. So, as a result what you have is a unit cell where A and B are the same, the angle between them is 90 degrees and C can be longer. Okay, sorry. So, let me draw the C. So, this is A, this is C. However, the B axis is in the unit cell, the B and A are exactly similar in length. Okay. So, you have A C, whereas A equal to B and alpha equal to beta equal to gamma equal to 90 degrees, right. So, it looks like it is slightly, the unit cell has more constraints than an orthorhombic unit cell. Orthorhombic unit cell does not have any constraints on the lengths of the unit cell vectors, whereas the tetragonal unit cell has a constraint, an added constraint that A equal to B, right. So, this is more constraint than an orthorhombic unit cell. Now, I am again let me emphasize that so this is I told you that unit cell can be defined in several ways, right. So, there is no unique definition of a unit cell, but here I am saying no, an orthorhombic unit cell should have alpha equal to beta equal to gamma equal to 90, a tetragonal unit cell should have A equal to B, alpha equal to beta equal to gamma equal to 90 degrees. Now, this is a preferred choice of unit cell, right, preferred because if I select my unit cell this way, right, so which I can, then I am actually going to represent the underlying symmetry, which is a fourfold axis of symmetry. I can select unit cell in some other way which does not actually represent this symmetry, right. Then just by looking at the unit cell, and unit cell needs to be periodically repeated to get your lattice, but just by looking at the unit cell I need to understand the symmetry properties of my crystal, right. If I do not get it, then that is not a very good choice of unit cell, at least when you are doing crystallography, right. When you are doing solid state physics, that is a different matter, but when you are doing crystallography, you want to actually see in the unit cell that you have defined the nature of symmetry that is present, right. So, if I am saying I have a tetragonal system, the fundamental postulate of a tetragonal system is that I should have at least one fourfold axis of symmetry. Then I need to define a unit cell such that I at least get one fourfold, so the unit cell itself represents this one fourfold axis of symmetry, okay. And that unit cell, right, so turns out to be constrained in this fashion, right. So, that A equal to B and alpha equal to beta equal to gamma equal to 90 degrees, right. So, this becomes a preferred choice of unit cell, okay. But you can always define unit cells that do not represent the symmetry of the system, and that is okay, right. But so for us to understand the crystallography and whatever follows crystallography, it is better to define unit cells that follow the symmetry of the system, right. So, as a result there are some constraints that come on the unit cell, okay, fine. So, that is a tetragonal system. Now, what has more constraints than a tetragonal system? This is what is our favorite system, which is the cubic system. Now, cubic system is perhaps the system that is taught the most, cubic crystal systems in metallurgical engineering, in physics, etc. But turns out that in terms of symmetry, cubic systems have a lot of symmetry operations, and becomes so to keep a laundry list of them and to understand cubic systems is so is more complex from a symmetry point of view, right. So, because of the sheer fact that there are a lot of symmetry elements in a cubic system, okay. However, okay, so we will get there eventually, but so it is not as simple as the unit cell looks like, okay. Now, so fundamentally what are the symmetry elements required for me to call a system as a cubic system? It is so because cubic system, the unit cell, you may remember from other courses, is just a cube, right, and a cube seems to have fourfold axis of symmetry, and not one but three fourfold axis of symmetry. If I draw a cube like this, right. So, this will be one fourfold axis of symmetry. This is the C axis, this is the A axis, this is the B axis, right. So, it looks like, if I am just looking at the unit cell, right, but I cannot say the symmetry just by looking at the unit cell, I should also look at the motif, right. But it looks like if I just look at A, B and C, it is a cube, right. So, well, there should be I rotate this by 90 degrees in any different direction, right, it is I should get exactly the same cube, but that is not necessarily true. What is true is if I have three fourfold axis of symmetry, that will be a cubic system. What is not true is for any cubic system you need three fourfold axis of symmetry, right. So, what you instead need is the necessity for a system to be called a cubic system is not three fourfold axis of symmetry, rather necessity of underlying symmetry is not three fourfold axis of symmetry, but rather, or 4 bar, right. So, 4 or 4 fold or 4 bar, rather it is, sorry, let me use this. For three-fold axis of symmetry. Okay. Okay. And it turns out I am going to so before actually showing you that A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees, it turns out that if you have a cubic unit cell, these threefold, okay. Well, I have not yet shown to you that what are the constraints in this cube, but you all know of course from other courses that in a cube A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. Now, this will come from having 4 threefold axis of symmetry. You do not need 4-fold axis of symmetry at all for you to have a unit cell which is a cube. All you need is 4 threefold axis of symmetry. Now, where are these axes of symmetry? If you imagine a cube, these threefold axis of symmetry are along the body diagonals of the cube, right. So, this body diagonal is one threefold axis of symmetry, right. How many such body diagonals are there? There are 4 such body diagonals in a cube, right. So, then the second body diagonal is somewhere this, right. So, this is the second body diagonal. Then the third body diagonal is between these two ends, whichever I am going to point it to be red, right. So, those two red corners, if I join that, that will be the third body diagonal. The fourth body diagonal I am going to point it in blue, right. So, this is the fourth body diagonal. So, that way and that way, right. So, this is the third body diagonal, which I am going to probably I can try to draw it, but this is well okay. Okay. So, these are your 4 body diagonals, and about these axes I have a 4-fold axis of I have a 3-fold axis of rotation or a 3-bar axis of rotation, right. So, or a 3-bar symmetry. So, in general a cubic system by definition, right. So, the underlying symmetry that gives you a cubic system is 4 3-fold axis of symmetry and not 3 4-fold axis of symmetry. Okay. So, now, I am so if I have a 3-fold axis of symmetry and these directions so as per Miller indices are 1 1 1 directions of a cube, right. So, I am going to use this, right. So, there are 4 3-fold axis of symmetry, but about 1 1 1 axis of the cube, not about the 1 0 0 axis. So, if I am going to use that matrix, right. So, if I have a vector x y z and I am going to transform it using a 3-fold rotation about 1 1 1 axis, right. So, the matrix of transformation so x a plus y b plus z c then transforms into z a plus x b, sorry, everything changes, plus y c, right. So, that is my transformation essentially. So, the matrix of transformation 0 0 1, right, 1 0 0 0 1 0, right. You can derive this, or you can go and look at the appendix, I think appendix 2 of the book Glaser and Burns, or Burns and Glaser actually, right. So, in which so all the transformation matrices for various symmetry operations are given, right. So, you can just take that table. If there is a problem that you have to solve, you can just use that table, right, and then so there is no need to mathematically derive these transformation vectors. You can do it once or twice for fun, right. So, but in general you can just take it off from there and then proceed further, right. So, look at how one vector transforms to another vector and what can be so whatever the problem demands. Okay. So, all these transformation vectors are there. Okay. But I also have a 3-fold axis of symmetry about 1 1 1 bar. Now, 1 1 1 bar would transform x a plus y b plus z c into y a minus z b plus x c, right. And so, I mean you can actually understand you can write the transformation vector from here, but in general I think so one thing I am doing is, and then similarly I can write transformation vectors for 1 bar 1 1, and I have another 3-fold axis of symmetry for 1 1 bar 1, right. So, what I am essentially doing is, okay, so then I can take dot products, right. So, so first of all I have exchanged so I am just going to argue based on what we did for tetragonal systems and what we did for the orthorhombic systems before. So, I am exchanging. So, by all these threefold rotation operations, every time I do a threefold rotation of operation, I am exchanging x to y or y to z, right. So, the indices or the coordinates of ABC are always exchanging upon transformation. And this we said can only happen if A equal to B equal to C, right. I mean, I can do all sorts of permutations and combinations of exchange. X goes to Y in one transformation, x goes to Z in another transformation. So, A equal to B, A equal to C, right. So, you can select that appropriate transformation. I am not going to do the complete problem, right. Also, so we have a change in sign, right. So, for example, yeah, so if so if A equal to mod A equal to mod B equal to mod C, then so I have I can just take dot products wherever so A and B get exchanged, right. So, mod A equal to mod B equal to mod C, but when there is a sign exchange, I can take this dot products and then I can actually show from dot products that so alpha equal to beta equal to gamma equal to 90 degrees, right. But these constraints are actually coming only because I have threefold axis of symmetry about the body diagonals, right. So, these constraints come about because I have there are threefold axes of symmetry about all the body diagonals. Okay. 3 bar also works, right, but 3 bar has an inherent threefold axis of symmetry if you go back and see the stereogram of 3 bar, but so 3 bar is okay. So, so I should have threefold. So, it's okay to say I have 4 threefold axis of symmetry and I have a cubic system, right. Okay. So, with that, let us stop this lecture here, and in the next lecture we will try to look at the trigonal and the hexagonal systems. There is slight bit of complication when we are looking at these systems, right, and then we go and address the topic of Bravais lattices. Why do we need to define what are called Bravais lattices? Again, to preserve symmetry, but this time we are actually in a given unit cell we are going to define what is called centering by so putting more than one point in a given unit cell. So, we will look at unit cells which are not what are called primitive unit cells. Okay. So, that we will do in the next class, and then we go towards looking at point groups. Thank you. So, I will see you again in the next class.